You press the handle, the bowl empties, and in a few seconds the evidence is gone. But that flush is not the end of the story. It is the beginning of a journey through pipes, pumps, tanks, screens, microbes, and laboratories. In many cities, the water you just used will spend hours being cleaned before it returns to a river, is reused for industry or irrigation, or receives even more advanced treatment. So what actually happens after you flush? The first machine in this chain is hidden inside the toilet. Water rushing from the tank pushes everything through a curved passage called a trap. That bend keeps a small plug of water in place after every flush, creating a barrier against sewer gases. From there, the flow enters the building drain and then the lateral pipe connecting the property to the street. Gravity does most of the work. Where the land is too flat or the pipe must climb, lift stations use pumps to keep sewage moving. Homes with septic systems follow a different route, but in a sewered city, thousands of small pipes steadily merge into larger ones. Underground, wastewater becomes a mixture of toilet waste, soap, food particles, laundry water, and whatever else people send down a drain. That last part matters. Wipes, grease, cotton swabs, and other trash do not simply disappear. Even products marketed as flushable can fail to break apart quickly enough for real sewer conditions. They can snag, combine with fat block pipes, and wrap around pump equipment. The safest rule is simple: only human waste and toilet paper belong in a toilet. Eventually the flow reaches a wastewater treatment plant. The first stage is not chemistry. It is protection. Bar screens catch rags, wipes, plastics, and other large objects before they can damage machinery. The captured material is washed, compacted, and usually sent for disposal. Next, the water slows in a grit chamber. Sand, gravel, eggshells, and other heavy particles settle while lighter organic material remains suspended. Removing grit early prevents abrasion and keeps it from filling tanks farther down the line. Now the wastewater enters primary clarification. In these large, quiet basins, the goal is separation. Heavy solids sink and form sludge on the bottom. Oils and grease float and are skimmed from the surface. Mechanical arms slowly move the collected material toward removal points. Primary treatment can take out a substantial share of suspended material, but the water still contains dissolved pollution that cannot be captured by settling alone. For that, the plant recruits an invisible workforce. In the biological stage, air is pumped into the water and mixed with communities of bacteria and other microorganisms. These microbes consume dissolved organic waste as food. They also help transform ammonia and other nitrogen compounds that could otherwise damage rivers. Operators control oxygen, mixing, temperature, and the age of the microbial population. The brown, churning liquid may look dirtier than before, but this is one of the most important cleaning steps in the entire plant. Billions of living organisms converting pollution into material that can be separated. The mixture then moves to secondary clarifiers. Here, the microbes settle into clumps on the bottom, leaving much clearer water above. Some of that biological material is returned to the aeration tanks to keep the system active. The excess joins the sludge from primary treatment. The clarified water may then pass through filters and is disinfected, commonly with ultraviolet light, chlorine, ozone, or another approved process. Disinfection reduces disease-causing organisms before the treated water leaves the facility. What happens next depends on the location and the level of treatment. Many plants release treated effluent to a river, lake, or ocean under environmental permits. Others send it to farms, parks, factories, cooling systems, or groundwater recharge projects. This does not mean every flush goes directly back to a kitchen tap. Ordinary municipal treatment and potable reuse are not the same thing. Water intended to become drinking water goes through additional barriers, advanced treatment, monitoring, and regulation. In some places, planned potable reuse is part of the supply. In many others, treated water simply rejoins the wider water cycle downstream. The solids take their own journey. Sludge is thickened and can enter sealed digesters where microorganisms break it down without oxygen. That process stabilizes the material and produces biogas rich in methane. Some plants use the gas to generate heat or electricity. After further treatment, the remaining biosolids may be used under regulated programs, processed into other products, incinerated, or disposed of. The exact route varies, but the goal is the same: recover useful energy and nutrients where practical while controlling pathogens and pollutants. Rain can complicate everything. Many cities have separate sanitary sewers and storm drains, but older areas may use combined sewers that carry sewage and rainwater in the same pipe. During intense storms, the volume can exceed the capacity of the network or treatment plant. Designed overflow points may then discharge a mixture of stormwater and untreated sewage to prevent backups into streets and buildings. That is why cities build storage tunnels, green infrastructure, and sewer upgrades, and why the result after a flush can change with the weather. So the moment the bowl clears, an enormous public system takes over. Gravity moves the flow, pumps lift it, screens protect equipment, settling tanks separate solids, microbes consume dissolved waste, disinfection reduces pathogens, laboratories verify the result, and operators watch the process every hour of every day. A flush feels like disappearance because almost all of the work happens out of sight, but nothing truly vanishes. It is moved, separated, transformed, tested, and returned to a larger cycle. That is what really happens after you flush.